Thank you very much for the introduction, and thank you everyone for coming to my talk. I also would like to express my sincere gratitude to the organizers who put together such an event, amazing event. The lineup of the speakers for this workshop is absolutely amazing, and I feel very grateful and honored to be part of this event. So what I plan to talk about today, as you can see, is mathematical analysis and for quantum simulation. So I will talk about quantum simulation. However, it's more about closed system, not quantum open. So it's sort of out of equilibrium for this workshop. So hopefully, later talks will be will thermalize and go back to the open story. And I will be based on my talk on these two works that are in collaboration with Xiaoxi Wu from Australia National University and A.V. Soffer from Rutgers University. Just a little bit about myself. I work on applied and numerical analysis. I also use some analysis tools from mathematical physics, say functional analysis, semi-classical analysis, and I prove theorems regarding quantum dynamics or quantum algorithm. That's the talk today is an example of what I do. So the outline will be the following. I will discuss about quantum simulation, which is going to be a familiar topic for most of us. And then I will motivate why we consider many-body Coulomb system. And then I will present two results. First is for general initial condition, and then improved convergence. So first of all, quantum advantage or quantum simulation. Why do we study these problems? Certainly, I believe a large part of the quantum community, especially the theory side, we are really intrigued by the idea of quantum advantage. In a nutshell, it means quantum can do things faster than classical. Well, what does can mean? It means algorithm. We need to design a good quantum algorithm, can be right into great quantum circuits and then hopefully realized by experiments. And then things means we want to have good applications that can be formulated into well-defined computation problems so that we can do something about it. Faster will mean cost or complexity estimate in a rigorous manner, which means theorem proving. And certainly, our hope is for any given computational problems, we can ask this question, is there a quantum advantage? Is there a quantum versus classical separation? Of course, the hope is that we hope there is a super polynomial separation or exponential separation. But in order to create, certainly we need to prove at least two things. First is quantum in the sense that we can design a quantum algorithm and prove that the complexity or the cost is upper bounded by poly n. Let's say n is the system size, the number of particles, maybe for PDEs is the dimension, and so on and so forth. At the same time, we also want to show this problem is classically intractable. Two criteria that are widely accepted for now. First is that if this is a well-studied computation problem by many people in many fields for many decades, for example, integer factoring, then we will trust the best known classical results that include all of the deterministic as well as the probabilistic problems. And then we want to find the bad instances in this computation problem class and show that the cost is at least exponential. Or if we can also show this well-defined computation problem is so-called BQP hard and a reasonable complexity conjecture, we do not expect to have a polynomial algorithm. Well, there are a lot of examples where we do have great separations and so on and so forth, including many topics that we have already seen in this workshop. But some of my favorite examples, such as integer factoring, quantum linear system algorithm, and Hamiltonian simulation. And my talk today will be focused on Hamiltonian simulation. So let's get started. Hamiltonian simulation, it just means I have a Hamiltonian that is time-dependent or time-independent, depending on what type of problem you are interested in. We can certainly write down the differential equation, the Schrödinger equation, which is just a linear differential equation with certain initial condition. And the task is essentially translated into I want to come up with approximate unitary. Hopefully it can be represented with a very efficient quantum circuits. I want to show that this algorithm can approximate my solution very well up to, say, epsilon precision. There's certainly an immediate estimate we would like to make. Usually we will make this because all of the wave functions are L2 normalized. So we will focus usually on the operator norm of the Hamiltonians. If you can show this is true with theoretical guarantees, it will account for any initial condition as well as any observables that you have in mind. So sorry, similar for time-dependent. Of course, the goal for us, there are various goals, but one of the goals is that we would like to show the cost, say quantumly, is actually polynomial dependent. Let's say on the system side or on say, the spatial dimension or on some other parameters that you have in mind. Certainly, this is a very celebrated algorithm problem dated back to the original motivation why we want to build a quantum computer. There are amazing lineup and significant work along this line, and many by the audience in this room. I decided not to give because otherwise it's going to be like too long. I do not want to accidentally miss any significant contribution. But the point or the takeaway is roughly that you will have a quantum circuit that is efficiently represented in a polynomial n, say the number of the number of particles, the system size, or the number of qubits. And how many times you need to run the circuit is typically polynomial dependence on certain operator norm of the Hamiltonian itself. So indeed, when the Hamiltonian is bounded, say it is only polynomial dependence on n, and we have great applications and a great algorithm, all of the upper bound, lower bounds, amazing contributions from various different scientific communities and so on. But my talk today is more about what if the Hamiltonian is unbounded? Well, what do we mean by bounded? If our Hamiltonian is bounded, it means that the operator norm is going to be infinity. So you immediately realize that I have some operator norm dependence. If it is actually infinity, like how do we make sense of these finite dimensional results? That's what I'm going to discuss today. But before that, certainly you can be like, okay, but why do we care about unbounded operator? If there's no applications, physically absolutely irrelevant, then you don't need to care, right? Certainly, unbounded operator appears in various applications. For example, quantum chemistry, electronic structure problem, and the molecular dynamics in, say, for non-adiabatic dynamics and so on and so forth. And also, it can come from with, you want to design some quantum algorithm, say, continuous variable optimization, where you can design a Hamiltonian simulation operator of this form to simulate this algorithm. This is also a significant line of work done by the audience in this room. The point is that Laplacian plus potential, this is an operator that is unbounded. In other words, the operator norm is actually infinity. So what exactly is an unbounded operator? On a formal level, you can see the following. H is an unbounded operator in the sense that I have a Hilbert space. Typically, it's an L2 Hilbert space because all the wave functions lives there. And there might exist some in the Hilbert space that after you're passing through the operator is no longer in the space. In other words, if you look at the operator norm, it's going to be infinity. That's the unbounded that I'm going to talk about here. What are the examples? Certainly one example can be differential operators, say the Laplacian operator that I showed you on the previous page, where all of the wave functions are living in the L2 space. You can easily cook up an L2 function whose second derivative is not bounded. So immediately you realize it's an unbounded operator. So what I want to say is that unbounded operator will only make sense on a domain which is sub-Hilbert space out of the entire Hilbert space. It will not make sense of the entire Hilbert space. That's the definition of unbounded. Well, you may argue with me, you can be like, the unbounded, the difficulty, I think is not really true. It's not really there because I can always discretize it and everything become bounded. What's the big deal? Well, yes, you can discretize it. This is just some simple illustration using m degrees of freedom, where the point is the operator norm is polynomial dependent on m. And then you can certainly go ahead and do your error estimate and so on and so forth. You will realize everything is polynomial dependent on m. You send it to the continuum limit, it's blowing up, and you are not solving the problem. You are just maybe delaying the problem to further consideration. Also, polynomial dependence is can cause you more trouble, but that's a story for another day. So the major question I would like to consider is for unbounded operators, can we still show that the simulation is quantumly efficient in the sense, is the approximation error polynomial in the system size or polynomial in the spatial dimension if you are dealing with a PDE setting, or polylog in the total degrees of freedom for the numerical discretization? Well, there has been significant work in the community, especially in recent years, addressing unbounded operator challenge, including many people, again, in the audience, as well as myself. And I would say, typically there are two ways. One is that we do this specific case analysis. Instead of looking at the worst case scenario, which will work for all of the initial condition, all of the observables, you want to propose some additional properties that the initial condition or the observable might follow. It can be locality, it can be some regularity, it can be initially start from the low energy subspace and so on and so forth, or some symmetry. Essentially, I would think the specific analysis, the whole takeaway, the idea is always that you want to find some conserved quantity or almost conserved quantity of your dynamics, and you somehow want to conjugate all of your estimates towards that, and then you can play around with the dynamic simulation, get a much better improved estimates. And the other way is by this interaction picture. As I said, the answer is yes, only for bounded or smooth potential. So for interaction picture is that I have a bounded operator, which is Laplacian, but I have bounded potential. So you can turn it into interaction picture by rotating this unboundedness, and then you will end up with a time-dependent Hamiltonian that is actually bounded because your potential is bounded. So you do need some room where your operator there is a bounded part to play around with this game. And then, because it's time-dependence problem, you will need to use a time-dependent simulator, although your problem originally is time-independent. That is also something people has been looking at. But before I move on, I think one interesting thing to mention about unbounded operator using interaction picture, which typically people do not discuss in great detail, is that it is well known in mathematical physics community, for example, due to the standard physical functional analysis textbook Samuel Reid. There was a session dedicated when you have unbounded operator, interaction picture may not make sense in the sense that you have the original picture equal to the interaction picture, but the new interaction picture operator will only make sense on certain domains. Sometimes the domain is totally different from the original Schrodinger equation that you start with, or sometimes the domain can be an empty set. Even if you solve it, it's not clear what happens with the original picture. So there was some issue regarding that. Where in one of our previous paper, we write a few discussions in these cases why interaction picture is actually making sense. But that's not what I'm going to really focus today. The question for today is, what if the potential is also unbounded? So I have unbounded plus unbounded. There's no wiggle room for me to play around, make things bounded. Particularly, Coulomb potential is going to be what I'm going to focus on. You may wonder, why do we care about them? If there's, again, no physical relevance, we shouldn't care about them. So the first principle many-body Hamiltonian, or you can also consider the electronic structure problem, the point is that you have a bunch of particles. All of them are interacting in this Coulomb potential behavior, where Coulomb potential is -1/r, where you can see as r goes to 0, this non-bounded also is long range, and it is not smooth. You have a lot of issues with the Coulomb potential. This is a natural many-body potential one should consider. Well, it's also nice just to mention this multi-scale pictures in terms of PDE, please.
I just have a question about the Coulomb potential. So is it because you are using a different discretization? So for example, I'm not sure, so I might be wrong. Typically, my understanding of the electron structure is they use second quantization.
Yeah.
And the norm of the Hamiltonian is naturally bounded by.
Yeah, you can view, I will view second quantization as a specific way to discretize the first quantization Hamiltonian. They should be equivalent. Still, you can try to send it into the continuum limit. It wouldn't change the fact that in the continuum limit, things wouldn't converge. You can say I truncate it at a finite dimensional space, and I'm going to treat the number of degrees of freedom n, or the quantum number, as a constant that is intra to my algorithm. You can say in the end you have polynomial dependence on that. But what I'm trying to address today is the continuum limit. Very good.
So when you say continuum limit, it's you make the number of orbitals to be effective.
Exactly. As you will see later. Thanks. Okay. So just to connect with the multi-scale PDE, if we would like to choose one PDE model as the model and say all of the other can be viewed as a certain approximation of the original model under certain regimes, then it's the many-body Schrodinger equation as the fundamental model, and then you can pass along the limits where you will have classical mechanics, statistical mechanics, Boltzmann equations, kinetic equations, or fluid dynamics, and so on and so forth. This is intrinsically the Hilbert 6 problem, and I took this particular page, this figure from my thesis advisor, Professor Chili's slides. It's also nice to mention, just as a motivation, why many-body Coulomb system is important. We can basically quote Paul Dirac, and the whole part of a large part of physics, the whole part of chemistry is known, and then the difficulty is solving them. I'm not going to discuss on solving. So now concretely start of what I'm going to concretely focus on, the well-defined computation problem. I'm going to consider this many-body quantum system with Coulomb potential. Specifically, this n is the number of particles that I have in this system. Each of them live in a three-dimensional space, so the total dimensional space is 3n, where n is the system size. And then you could imagine this is a 3n PDE naively discretization. This should give you some sort of, some error that is exponential scaling in these parameters. But we will show it's not. So the Hamiltonian is just a kinetic part, which is the regular kinetic potential. And this Coulomb interaction is the same Coulomb interaction that we use in the physical model. It's exactly the same. It's just that this CJK represents the electronic or nuclei charges. And I'm allowing the CJK to be either positive or negative. All I need is that they need to be some finite number. They cannot be infinity. And this, the bounds of this number, I'm going to say, is called C0. It's, they can be anything, as long as they are finite number. So by allowing positive sign and the negative sign, we can account for electronic structure problem and also molecular dynamics, because we can account attractive, repulsive, or a combination of both. So the concrete thing that I'm going to prove is this question of how fast does trotterization converge in the continuum limit. Trotterization, of course, everybody is familiar with it. But then you may wonder, why do I care about trotterization? Because there are great other algorithms out there in terms of quantum simulation. Why don't we consider that? So first of all, trotterization, this is an illustration of the Lee-Trotter first-order trotter. This linear in T, where T is a small time step, means it's a first-order convergence. It has a commutative scaling, as is well known in the community. Some of the history worth mentioning was that the Lee, original Lee and Trotter, they were actually not really studying a numerical algorithm at the time. And then Gilbert Strong, I believe, was the first person, applied mathematician who recently retired from MIT, proposed to use this as a numerical algorithm and did numerical analysis to it. And later, Suzuki generalized it, said that we should use it for quantum algorithm and develop great development for quantum simulation, and then this celebrated work for computer scaling, and so on and so forth. Certainly, there are more work should be cited here, say Kato and so on and so forth, but these are some. On the other hand, I will call the other type of quantum simulation algorithm, Hamiltonian simulation algorithm, altogether as the post-Trotter algorithm. There are many of them anymore. The point is that the post-Trotter algorithms, they all involve the block encoding, where the subnormalization factor is guaranteed to be bigger or equal to operator norm of H, and I'm dealing with operator norm of H is infinity. That's why in the unbounded scenario, you have unbounded plus unbounded, so trotterization might be the natural choice. And now let's think about why typical Trotter analysis fail. This Trotter has more than a century history, and many people have studied it. We certainly know a great deal about how to deal with the analysis, so what's new? Well, you can think about the original Trotter analysis, where it gives you a nasty commutator scaling. Well, this is actually true when everything is bounded. And you can realize if I actually directly use this bound form just for one body case as a simplicity, you can immediately realize this is, again, an unbounded operator. You have infinity. Your right-hand side is trivial. It's just infinity. It do not tell you anything. Then you may think, OK, I can maybe still borrow the idea of these great results, and maybe I can massage the idea of the original proof just a little bit. And then I can still deal with this unbounded operator. So this was original. It takes you like 2 variation of constant, about 3-line proof to get here. You can rigorously show this is the error exact representation is exact. There's no error being made and so on and so forth. I'm not going to talk about that. But this is how you show it is actually nasty commutator scaling. And here I want to bring up an important thing, which is the major takeaway. If you work away from my talk, just remember one thing. I hope you remember this, is that every bounded operator I will like to say my personal opinion is all bounded operators are created equal, but every single unbounded operator is different. In the sense that when we have bounded operator, finite dimensional operator, it will always map the Hilbert space back to the same Hilbert space. You don't need to worry, oh, it's not making sense and things like that. So whenever you have these unitary operators, the operator norm are all gone. They are just one. So you just take the operator norm, everything is gone, you easily immediately get that. It's just couldn't be simpler. However, for unbounded operator, as I said, it only makes sense on the domain, not on the whole Hilbert space, only makes sense on a sub-Hilbert space that you need to be careful. And then when you pass along this bound, for example, suppose this is going from a sub-Hilbert space to the whole Hilbert space, but then it's not in this domain anymore, then you cannot keep going. The whole equation is just not going to make any sense. So then you will then try to ask yourself, what happens if I map this unitary operator from the domain to its domain? So immediately, I can tell you the operator norm is certainly not 1, well, unless you have very special cases. So it can be easily n-independent for our many-body Schrodinger equation, which will be one of the estimate in gradient that I will show. It is actually n-independent. Or actually, if I just have an exponential of this Coulomb potential itself, it will not map my domain back to domain at all. So that operator is actually infinity. So you cannot even make sense of it. In the sense that if you really want to massage this error representation somehow, you cannot have this B, which is the Coulomb potential. It has great singularity on the right-hand side. Because once you have B, you are pushing everything outside of the domain, and then it's difficult to make sense of the rest of the terms. So as you will see later, I will try to avoid having B on the right-hand side. That's really crucial in one of the estimation steps, although it's not the most important step. So here is our result. I'm going to consider any n that is the number of particles, which is bigger or equal to 1. I never use any fact that other than n is a number that is bigger or equal to 1. And then for the state, I'm going to consider all the states that is in the domain of the Hamiltonian, so that the Hamiltonian is actually making sense. So although this seems that I'm not considering all the Hilbert space, but this is all the wave function that is actually making sense. So this is not a specific case estimate. This is the general case estimate. Work for any initial condition in the domain.
Sorry,
and then
you say the domain of the Hamiltonian, right? H is A plus B, right?
Yes.
So you're really assuming that that one is a closed operator, and you're taking the domain of that as the closed operator.
Yeah, A plus B in the Coulomb potential. That's the H2 is the domain. That's the domain.
Oh, okay.
Yeah,
so
yeah,
this is specific to the Coulomb potential.
Yeah, exactly. That's very good. Yeah, I'm specific. Thank you, Dima. And then I'm looking at the long time like before. This is the first error Trotter error representation. The C is a absolute constant that will only depend on the C naught, which is the Coulomb charges, the upper bound of the Coulomb charge will depend on nothing else. We actually gave you in our paper explicit numerical value of that, but I would like to emphasize we made no effort. We just wanted to say there is a universal constant. We made no effort in optimizing this constant because we are really focusing on polynomial in n. For example, if I have 100n plus 2n raising to the 4.5, I will just say, okay, 102. I'm not using any properties in terms of anything to try to, I did nothing to optimize this constant, so the constant is definitely not sharp. And this n raising to the 4.5 power will just coincide with the idea is that it's quantumly efficient. Interesting to note that comparing to, I truncated in a finite dimension. I'm working with continuum system in the first place. If you truncate it into finite dimension into finite grids or finite orbitals, and then you send the orbitals, you take the continuum limit, you wouldn't get anything bounded on the right-hand side. But what I'm saying is it's actually you can tolerate a large time step, and it is actually bounded, not so sensitive to how many orbitals you are using, please.
So what's this n? So in your formula, everything is continuous, right?
Yeah, everything is continuous. This n is how many particles there are in the system. So the whole Hilbert space is R raising to 3n. Is L2 of R raising to 3n. The spatial PDE, the spatial dimension of the PDE is 3n.
So then what do you mean when you say phi 0 is in H2?
Oh, yeah, I will explain that later. Yeah, so please.
So for the left-hand side, what's the norm?
Oh, the L2 norm.
L2
Thanks.
norm.
Yeah, because that's usually what we use, the L2 norm. Thanks. So this is n to the 4.5 power, and this is t raising to the quarter. As has been seen before, the power of t tells us how fast the Trotterization is actually converging. As you can observe immediately that we know first order Trotter always converge first order in terms of bounded operator. And for a lot of unbounded operator, as previous cases has been shown, you can also show that some of them are still first order. But in terms of Coulomb singularity, it turns out it's 1/4. You can immediately ask, is that my bound is not tight and so on? It is actually sharp or optimal if you'd like, which previous work, which I will show you later, has demonstrated that the ground state of the hydrogen atom actually accentuate this 1/4 growth rate in one body case. So now let me discuss a little bit about this H of H2. This is like a condition, only depends on the initial condition. So whenever we are writing an estimate, of course, you can write the right-hand side into the solution at time t and so on and so forth, but that wouldn't be a quantity you a priori know. So for us, the allowable bound is only if I have initial condition, some quantity uniquely determined by the initial condition. That constant can be a real constant. So alternative theorem, if you do not like this Sobolev norm H2, you can just rewrite it into, I'm not using norm equivalence. You can use similar step and to reprove this theorem, this is H acting on psi naught, which is a conserved quantity. So whichever way you prefer. So now I would like to address a number of questions or discussions regarding our result. First of all is that I said this 1/4 rate is sharp or optimal, however you would like to call it. Usually we know that in the algorithm analysis, if something is optimal, usually the worst case, not always, but sometimes the worst case is typically a cook-up example that you wouldn't encounter in reality. So some physicists may come in to say, hey, we don't have that in reality. Theory works great, but I just wouldn't encounter that. But is that also the case for our particular many-body Coulomb potential? That's actually not the case because the worst rate, 1/4, is accentuated by the ground state of a hydrogen atom. If you agree with me, ground state is going to be the most physical state. So that's the worst case scenario. And you may also wonder, hey, I'm looking at infinite dimensional system in a continuum limit. Isn't this just irrelevant if I consider finite dimensional spatial discretization? Well, it is actually not irrelevant. This was the significant work that was specifically dedicated to this problem, where they looked carefully at the numerics and also did physical analysis to that. So what you can see, this is their numerical graph. What you can see is that I'm choosing different, we're choosing different number of modes for spatial discretization. If your number of modes is just 100, which is not going to be consistent with the physical reality because your original problem is PDE, 100 modes is too small of a size to represent what the original infinite dimensional system really is. You get this rate, which is 1/4, but as you raise the n, the number of bases you are using to go upper and upper, so you are realizing more and more of the physical reality, you get some tilted lines, so on and so forth. When you do the extrapolation, you get this line, and that is 1/4 rate. Specifically, you can realize there was some turning points here, and these turning points from their simulation will grow significantly as you increase the number of modes, or you use a different cutoff to the Coulomb potential, or it's also presumably we believe that as the system size grows, this will also grow dramatically later on. So this is actually you actually see this in your simulation. Okay. So the next question, which is again, as I said, that the super large, so what our result is saying that in the continuum limit, you might think it will not be finite, but we show it's finite. This would imply you can tolerate a potentially much larger time step that is not so sensitive to how many orbitals or how many bases you are using in this discretization. So the next natural question is there a physical intuition to such a Trotter convergent downgrade? Instead of first order, now it's a quarter. So it was also mentioned in this paper saying that it's really because the Coulomb singularity will cause the wave function to have cusps. So the cusps are really bad. They do not give you good error bounds and so on and so forth. And those causes this unsmoothness of the cusps that causes the downgrade. So again, just to emphasize, from my perspective, all bounded operators are created equal. Every single unbounded operator should be treated differently. So now let me just discuss more mathematically where does this downgrade came from, or concretely, why is this magic 1/4 rate? So I can give you a mathematical explanation, very simple explanation of that. So this is the Coulomb potential. Unlike many of the analyses, it's not bounded from below, it's not subquadratic, it's none of that. It is singular, it is long range, and it is non-smooth. So it's the worst potential you would like to consider, but this is the physical reality. It is well known that if I split it into two parts, so this part, although it's singular, it is actually L2. The remaining part, although it's long range, but it's actually bounded. It's actually L infinity. So Coulomb potential is L2 plus L infinity. Typically, people split it using a constant, say constant equal to 1. But if you do that, you wouldn't be able to get a 1/4 rate. So what we realize is we are going to do the cutoff with respect to S, where S is a short time step, raising to a beta power. And beta is going to be something that I want to determine next. So as you can see, there is a regular part, which is this part, long-ranged. There is a singular part, which is this part. So naively speaking, there's many things should be made rigorous, but naively speaking, the regular part will, depending on where you cut off this beta, will lose a little bit of the convergence due to the cutoff places. And the singularity due to the beta will gain a little bit of convergence due to the cutoff places. And then when you add them together, you want to choose the best bounds you can possibly get. You immediately realize beta is 1/2. That's how you get a 1/4. I think at this moment, it's also nice to just mention that when dealing with Coulomb potential, people sometimes will regularize it. We will deal with regularized Coulomb, modified Coulomb, Coulomb Yukawa potential, or some pseudo potential. Those potential will assume the singularity is just not there. So if you take that picture, for example, for Yukawa potential, essentially says that up to this beta equal to 0 of order 1, my potential is always going to be regular. So if you put that scenario here, you will see that, okay, I indeed have first order because beta is 0, but the singular part, if it is there, it's not going to be convergent at all. So this is really this play around these two parameters where it gives you the 1/4 rate. And we are certainly not the first ones study this one-body case, this 1/4 rate. There are two significant results on this particular line. The first result was the one also produced very carefully the numerical results, which I mentioned in the previous slides. There's also a group of mathematical physicists. This celebrated work was accepted in International Congress Mathematical Physics in 2024, where they look at the first order cases and for general initial condition in one-body cases. But you couldn't get a sharp 1/4 rate. You can get very close to 1/4, but you couldn't, for one body case even, you couldn't get a 1/4 rate. So this work, this mathematical physics work is based on forward space and the interpolation of the forward space. This is a very beautiful paper, long and giving you all of the interpolation properties one would expect, and that's but where our technique is completely different. And also, you could imagine you can extend these one-body scenario analysis. You can try to extend them into many-body, but none of these techniques are going to tell you what's the system size dependence. Because if you imagine you are doing interpolation or you are doing some norm equivalence, you are saying you can very likely introduce the system size dependence. Just one analogy, not quite right, but a simple example, just think about finite dimensional. L2 is equivalent to L infinity norm, but there's constant can easily introduce the Hilbert dimension, the size of the Hilbert dimension. So you need, when you want to show you have polynomial dependence on the system size, you need to be careful about these norm equivalence or interpolation that you would like to use. Please.
You mentioned Yukawa, but I missed something. I mean, if you replace the Coulomb,
yeah.
Yukawa, which then still has this Coulomb singularity,
yeah.
but it has rapid decay, exponential decay,
Yeah.
which is usually physically motivated by screening.
I realized that's
Right.
I should have said
So if you did that, then it would change your interplay between these things, because you would only have a short-range problem. What would that do to the 1/4 if you replace Coulomb by
It's going to be better than 1/4, but I need to sit down and look at the domain to make sure consider. It should definitely be better than 1/4. I think it's likely going to be just 1. It could be.
I think 1, 2, right.
Yeah,
so this 1/4 is coming from the 2.
The tweener. I should. You're right.
But in a many-body problem, you would expect, if it's neutral, you would expect screening, right? And then that should get rid of the long-range problem. So if you have charge neutrality in your estimates, then you might hope there would be screening. Can you get a better result? I mean, your charges.
I will tell you like what are the conditions I can propose to get a better result. That's the second part of my main result. But this is for general. I'm not assuming anymore. Yeah.
Right, but you would expect if you had unbalanced positive and negative charge, then the situation should be.
That will. Yeah, I agree. That's one of the open questions. I will. Yeah, please.
Maybe related to that. So in the setup, you don't have the nuclei, right? Is that
sorry, in the setup,
you don't have the nuclei. This is
so this is one body illustration. I'm dealing with general n-body, in which case you can have the nuclei, you can remove the nuclei, whichever case it will work. So here is a one-body illustration, tell you nothing about n-body.
Yeah, I'm just asking so that for the theorem that you state, you can have.
I can have all electrons, or I can have electrons and nuclei all together, or whichever, or you can have quark, or as long as.
So the n-body theorem had nuclei and electrons.
Yeah, sure.
But any number you could do. There's no
exactly.
Yeah,
sure. And so just a little bit more about how the regular part in the singular part work out. So I would like to say in our case, unlike the previous significant work in one body case, first of all, we get this sharp 1/4 rate. And also if we just do one body case, interestingly, we write it in our appendix, there's only one lemma we need to prove, which is less than 2 pages. It's like roughly 1.5 pages. We prove more around the one body, just as an illustration how we do general body. But if one body is like 1.5 pages is going to be sufficient. So these are some just naive, immediate illustration of how exactly you should get that two-body computation. So for example, here I have Coulomb potential, which is roughly 1/x, and 1/r, where I'm taking second derivative, roughly give you this. And then if I look at the L2 norm, it will be 6 power, and because it's 3 dimensions, so the dx become r squared dr, roughly speaking. And then that's how you get this. And you have a 1 because of the integral. That's how you get the first term. The second term is similar, where you can have this. You have the singular part where you can easily use a volume estimate, which will give you beta divided by 2. And here you have some L infinity where you can take care of these by Sobolev embedding bounded by H2, where you can explicitly quantify the constants, not saying there exists constant. You can write out precisely that constant. So these are just some part for one body case, which is, if you're interested, look at our 2-page proof. But the core estimates, also the mean result I'm presenting is not for one body case, it's an n-body case. So most of the technicality really comes in to quantify this n dependence. You have a bunch of constants, but how does this constant depend on n precisely? So this is the main difficulties. So technicality speaking, there are 3 new ingredients that I believe are all of independent interest. The first new ingredient is alternative exact error representation for Trotter. Like the previous error representation that I showed you, which can immediately, by taking the norm, giving you the nested commutator scaling, you have alternative, you can further expand and make it there's completely equivalent. But as I tried to say before, I'm trying to avoid any expansion in terms of the Coulomb potential on the right, because that will be really unsingular. I want to keep the Laplacian on the right. I want to keep the Coulomb system on the right as much as possible. I delay this to the very end. So this is alternative and equivalent formulation. So exact error formulation is actually, I believe, well celebrated in the numerical analysis community. I just listed a number of famous work along this line. I'm sure I must miss some significant contribution. And then Charles Yuan and so on, they sort of extend these ideas into quantum simulations that are really, a great set of tools you can use. This is something good to have, but technicalities is nothing. It's really simple to prove. But then the second ingredient is the Sobolev norm estimate. As I said before, I want to say take a look at how does this the domain, two domain, how does this unitary operator, the bound of them. So Sobolev norm estimate, you may immediately think about, okay, the celebrated Bergin result and so on and so forth. But we focus on sort of different questions. So for their results, typically the potential is assumed to be analytic or smooth on a periodic boundary domain. And then you care about this time-dependent potential. How does this, what's the Sobolev norm growth in terms of time? But here, I'm not, the Sobolev norm growth of our system is independent of time. There's no time growth. But what we want to quantify is what is the constant in terms of n. So it's sort of a different question, although they all under the Sobolev norm estimate regime. So you can see, particularly this means that from H2 to H2, the unitary operator itself is actually n cubed. The third ingredient, which I find pretty interesting, this is a unique ingredient that I believe is a very going to be helpful property if you have other problems regarding many-body Coulomb potential. Maybe our property can help you. I call this a counting property, which is essentially a property regarding a Coulomb operator compensated with the momentum operator L2 to L2 bound, where you can write out exactly, and this bound give you n to the 3/2 power. So interesting to remark, in the one-body case, this will reduce to a celebrated Hardy's type inequality, or Hardy little Sobolev, if you like, and we can generalize it to the n-body case, which is one nice counting argument we use. And just regarding this 1.5, another thing to mention is that just recall that Coulomb potential has n squared terms in total adding together. So we are not getting n squared, we get n 1.5, which help us to get a better independence. So this is also something to note regarding this ingredient. So after that, I was pretty happy because I feel like, okay, now I understand. I originally came from multi-scale community where the many-body Coulomb potential is really my, with electron and nuclei is really my go-to problem. And now I was like, okay, I feel good. At least I can show what happens for the first order Trotter. And then the natural question is, what about higher order Trotter? What about second order Trotter? Do you get improvements? Maybe it's no longer one quarter, it got better. Well, so that's what we do. The technicality speaking, it evolves more because in second order Trotter, it's impossible to get remove all of the exponential in B unitary in the local truncation exact error representation to the left. So there are more technicality involved, but I will not discuss about that. The takeaway is really that you have the same bounds. It's still a quarter. Again, is it not sharp because of our mathematical analysis? Maybe not, because the previous numeric paper that I mentioned, they also did the second order, and they find it's actually 1/4 for hydrogen atom ground state. So we have, this is what we have. So what's next? The natural thing for us to consider is that first order Trotter, we expect to be first order. Second order Trotter, we expect to be second order. Somehow magically for this Coulomb singularity, things become 1/4. Then this is for general case, for the worst case scenario, if you like. Then can I impose certain initial conditions, certain set of conditions on the initial states, so that 1/4 is still 1/4, one order is still one order, second order is still second order. That's a very natural question to ask. That's what we did. So this is, the answer is yes. We currently have the analysis for one body or two body cases. For general n-body, I don't have the analysis yet. So if I cannot prove something, I cannot say, I would prefer not to comment on them. So concretely, this is the assumption we need to propose on the initial state. There is some projection operator floating around, which I will tell you precisely what they are. I'm not defining them for now. But just pay attention to this L. This L needs to be an integer that is bigger or equal to 1. Actually, when L equal to 0, this will correspond to the ground state sector. So I'm effectively saying, OK, remove the worst case, remove the ground state. That's going to give you a quarter rate. And here I have some funny regularity assumption where it's x raising to the L's power and H2. I will explain a little bit what this means later. But under this condition, what we can show is that the trotterization will still be first order convergence for first order trotter if L is bigger or equal to 1. For second order trotter, if L is bigger or equal to 3, I can still recover the second order trotter convergence. This was the result that we have. Now let's talk about what does these conditions mean. So first of all, I said that L equal to 0 is roughly speaking like removing the ground state sector. And also, you realize when I have L equal to 0, this term is gone, so I'm just treating the general case scenario. So that's why I'm restricting ourselves to L bigger or equal to 2, because L equal to 0 is just the general case, which we already studied. And then this part is sort of the regularity assumption, which you can sort of view it as how the solution is behaving initially, the initial state is behaving near the Coulomb singularity. If you have some regularity to play around with this singularity, and you can get an improved estimate. So the key observation, key estimate is really that this quantity which is assumed initially is actually a preserved quantity a long time. In the sense that initially if it's L2, it remains in L2 for all the time. That's what we proved. This is also consistent with the general idea of specific case analysis, as I tried to illustrate a little bit before, is you want to find some conserved quantity or almost conserved quantity and to play around with so that this quantity is preserved over time, and you want to convert your estimate into this quantity, which gave you an improved estimate. This is also an example of that idea. So physically, you may wonder, like, what does these finding L mean? Like, it's really difficult to interpret, especially if you're not so familiar with the PDE analysis. So I would like to say it's actually related to the orbital angular momentum if you think about the hydrogen atom. So again, hydrogen atom has uniquely this C, the constant, equal to -1. But my analysis is for general C, but I can still use the hydrogen atom to illustrate like physically what it means. This slide is just to say that the initial condition will propose there exists physical states that actually has this initial condition. So you can easily convert it into spherical coordinates, which motivate us to consider the eigenfunctions of the of this Laplacian operator. There are going to be spherical harmonics, and then your initial condition can be written as linear combination of those. The projection operator is just saying remove the lower degrees of freedom of the spherical harmonics, and then the eigenstates of the hydrogen atom can be actually written in terms of this format, because this is like this is really simple. And then you can just observe or just do some simple calculations saying that the angular, so this is the principal quantum number, angular momentum quantum number, magnetic quantum number. So the principal, the angular momentum quantum number actually determines the regularity condition that I discussed before. If you have that number bigger than L, then that's assumption will hold. For example, if you have 3 to 0, and your assumption will hold for L equal to 1. This is some physical illustration, but again, we are not using this as anywhere in the part of our proof. So more on the technicality. The second order trotter, beyond the first order trotter, where we need to use the cutoff, we need to use Sobolev estimate, and so on and so forth, there are some additional new ingredient. Of course, we need to reformulate the exact error representation, making sure the domain is okay, everything is making sense. I will not present what they are here. The second is the key property that I mentioned is that initially, if it's in H2, you can write out, you can prove this is actually true preserved, and you can also squeeze a Laplacian part here, and you can also show that you have some preserved quantity. And the third ingredient is a Hardy type of estimate, which maybe known or not known, we just did a simple proof to this, where if you have this quantity, and this is an absolute constant that we can quantify, and then this will actually help with our analysis as well. If you're interested, you can talk to me. I can show you why this is helpful. So we can also do two-body case. It's really because two-body case effectively is equivalent to the one-body case, and the corresponding assumption is almost the same. It's just that we are raising this power at this Coulomb interaction, which is the difference between two coordinates. That's what it is. And the corresponding result is the same, L bigger or equal to 1 first order, L bigger or equal to 2 second order. Okay. So now I'm ready to summarize. So essentially, I talk about many-body Coulomb potential, first order and second order Trotter, the worst case scenario, and what are the conditions we can improve. And I think the biggest takeaway, let me just repeat, is in my opinion, all bounded operators are created equal in this type of simulation analysis, and every single unbounded operator is different. And so future direction, what about spatial discretization? This is because if you think about in numerical analysis, spatial discretization is typically based on the Sobolev regularity. It's like I discretize a function, the more bounds I have on the derivative, it's going to be convergent faster. It's the same for spatial discretization. Why this become hopeful problem to rigorously analyze that? Because in one of the ingredients, we estimate the Sobolev norm, we gave a Sobolev norm estimate in terms of the number of system size. That's why I think we are ready to tackle this problem, rigorous spatial discretization for many-body Schrodinger. What's the estimate? And then certainly Q drift, I have n squared Coulomb potential. Can I get away with n? You may think this is very simple, but it's actually not quite, because if you think of a Q drift estimates, the way is you use a Taylor expansion arguments, and it's unbounded operator. Your Taylor expansion are not converged at all. You cannot use that. You need an alternative representation. So that's something I'm interested in working in. And also, if I have all electrons same signs, and these Coulomb potential are actually positive operators, you can certainly improve the independence. This is ongoing work. And also, there are some scale separation aspects. Let me not mention them too much. And also, what about unbounded operators? Because they are all different. So that's all for what I want to talk about today. Thank you for your attention.